In this lesson, we'll look at sections 7 through 9 of chapter 17. Let's think a little bit more about the meaning of delta G for a chemical reaction. We might think that we would have the lowest free energy possible or the greatest drop in free energy if a reaction went to completion. So symbolized by what we see over there with like a ball rolling down a slope. However, we can actually get lower free energy if the system goes to equilibrium, and that's symbolized by this diagram here. So rather than going to completion from A to B, we get this C here that is actually lower in free energy. Remember, at equilibrium, not only do we have products, but we still have reactants that remain as well. In the next section, we're going to look at free energy and equilibrium. So as we just said on the previous slide, we're going to have the lowest value of free energy when we're at equilibrium. So that is going to be the greatest delta G. So this is how we can actually define equilibrium from a thermodynamic standpoint when we're talking about the lowest free energy available. Compare this to how we talked about equilibrium with kinetics, and we talked about the rate of the forward reaction and the rate of the reverse reaction being equal to one another. So there's actually an equation where we can calculate delta G if we are not at standard conditions. So not at 1 molar concentration, not at 1 atmosphere for pressure, not at 25 degrees Celsius for temperature. And we're not going to work with that, but you can see Q is here, the reaction quotient that we talked about in the equilibrium chapters. And instead of Q, if you want to substitute K into that equation and set your delta G to 0 because we are talking about equilibrium, we get this new equation that we are going to work with that is on your equation sheet. And you can see the equilibrium constant K in there, and delta G is in there at standard conditions. R is the universal gas constant. We want the universal gas constant that's in joules. This is on your reference sheet as well. T, temperature, we want to be in Kelvin. And this time we're working with a natural log. So make sure we do natural log instead of the base 10 log. For K, we are always going to get a positive answer. Remember, we can have a really large K or small K, right? A large equilibrium constant or a small equilibrium constant. But still, delta G can be positive or negative, and this negative sign right here in the equation is going to allow that to happen. Let's say we wanted to solve for an equilibrium constant given a delta G. We could definitely do that with a little rearranging of this equation. We get e to the negative delta G over RT. Let's look at the relationship between the equilibrium constant K and delta G. When K equals 1, when you have product and reactant equally favored, if you think about the equation we just talked about on the previous slide, the natural log of 1 is 0, and then that whole side of the equation is a 0. So delta G equals 0. And that's when we are at equilibrium. If K is greater than 1, we've got lots of product. K is going to be really high in our equation. And we will get a negative delta G, so less than 0. That will be a spontaneous process. And if you think about, making a lot of product, that's what we've been talking about with spontaneous or thermodynamically favored processes. If K is less than 1, that means we have lots of reactants. And when we put small numbers in for K, when we take the natural log of a number that is less than 1, we get a negative, and then this negative here will give us a positive delta G, and this is not spontaneous. So let's look at a problem where we can utilize this equation. We've got some free energies of formation and some heats of formation in our table for our two substances that are in the chemical equation. We're going to calculate delta S, the equilibrium constant K, at 298 Kelvin, which is where this would be initially. And remember, that's kind of what that little degree symbol there is telling us. And then we're going to do an estimation for the equilibrium constant K at 3000 Kelvin. So first, to solve for the delta S, the entropy change, we can use this equation that we've been working with, delta G equals delta H minus T delta S. We can use our free energies of formation and our heats of formation to come up with our values for delta G and delta H. And then we can go ahead and solve for delta S. So starting with the delta G, we'll do the sum of the free energies of formation of the products minus the sum of the free energies of formation of the reactants. And we'll get 495.4 kilojoules. This is a positive value, so this is not spontaneous or not thermodynamically favored. We're going to do the same thing for delta H. For delta H, the sum of the heats of formation for the products minus the sum of the heats of formation for the reactants. 591.1 kilojoules there. So this is endothermic. And finally, we'll take those pieces of information, the delta G, the delta H, we're going to plug it into our equation for delta G and solve for delta S. Temperature is 298 Kelvin. Delta S will be 0.321 kilojoules per Kelvin. If you want to put it in joules per Kelvin, as you would typically see it, that would be 321 joules per Kelvin. Now that we know delta H, delta S, delta G, we can solve for the equilibrium constant in part B. We'll use this equation and rearrange it so we can solve for K. So this is going to be e to the negative 495.4. That was our delta G from part A. And we're going to divide that number by the product of the R value that's in joules, 8.314 times 298. But we got a little problem here because our delta G was in kilojoules. And this R value is in joules, and we need the units to match in order to cancel out. So you can either convert your delta G to joules, or you can convert your R value to kilojoules. We just need the units to match. So for delta G, I'm going to call this negative 495,400 joules, and then I can go and do my math. E is the second function of the natural log key on your calculator. And when you solve, you get 1.45 times 10 to the negative 87th. Very tiny, much less than 1. Very reactant favored. And that matches up with our delta G from part A being positive, a non-spontaneous process. So now for part C, we want the equilibrium constant K for a temperature of 3000. And we're assuming that delta H and delta S are not affected by a change in temperature. So we're going to go back to this equation. We need a new delta G in order to find a new equilibrium constant K, according to what we did up here in part B. And so we're saying delta H, delta S are the same, and our temperature now is going to be 3000 Kelvin. So we use 591.1 kilojoules for the delta H, just like we did in part A. We're putting in 3000 Kelvin for our temperature. And then our delta S, we also want that to be in kilojoules. We want those units to match. So we're going to put it as 0.321 kilojoules per Kelvin. And for delta G, then we get negative 372 kilojoules. So now it's negative at this higher temperature. So now we are looking at a spontaneous or thermodynamically favored process. So now we'll take this new delta G and we're going to bring it up to this equation here. Put that in for delta G. Remember, you want that to be probably in joules to match the joules on the R value. So that would be negative 372,000 joules. And it's a negative negative, right? So we're going to make that positive. We get a new equilibrium constant of 3.00 times 10 to the 6th, which is greater than 1, much, much greater than 1. And that corresponds with a spontaneous process, like we saw on the previous slide. So going back and thinking about this delta G equation again, our delta H was positive, we were endothermic. When we solve for delta S, we were also positive, so increasing entropy. So we're doing positive minus positive. And to get the answer to be negative for delta G, we have to put a high temperature in here in order to make this term higher than the delta H. So that's exactly what we saw when we went from 298 to 3000 Kelvin. We got that temperature up high enough to give us a negative delta G, whereas at 298 Kelvin, we were positive. Finally, we define delta G, the free energy change, as the energy that's available to do work. The amount of work that is actually obtained is usually less than the maximum possible because of energy waste. So when you solve for delta G, this is the energy that's available to do work, the maximum amount, but in reality, that's probably not really what we're going to get.